Я почну українською, хочу просто подякувати за запрошення і можливість привітати рідну кафедру з 60-річчям. Хочу також скористатися нагодою і подякувати всім викладачам мого часу, особливо Юрію Степановичу Самойленку, який був моїм керівником і працював на той час, викладав на той час на кафедрі, Юрію Анатолійовичу Дрозду, В'ячеславу Михайловичу Футурному, хочу також згадати Сергія Адамовича Овсієнка, Віталія Івановича Віщанського. Дуже їм дякую. І бажаю подальших наукових досягнень кафедрі, талановитих, хороших учнів. Дякую також організаторам, що в такі часи зуміли провести таку чудову конференцію. Дякую. And I will continue in English, so I will give my talk in English. So I'm going to talk about complexification, some abstract complexification of groups, and its relation, talk about its relation to spectra of certain algebra, which we call the weighted Fourier algebras. So I just want to say that this is a joint work, is written work with my PhD students, Olof Giselson, and some earlier work with Maya Khandihari from University of Delaware, Han Hee Lee from University of Seoul, Jean Ludwig from University of Lorraine, and Nico Sprong from University of Waterloo. Yeah, it may sound a little bit more like functional analysis, abstract harmonic analysis talk, but there are a lot of algebraic stuff inside, so I will try to list these algebraic aspects of this project. So now I cannot move. Doesn't work. Sorry. Oh, okay. Yeah, I will start with complexification of abelian group. So I consider G, so this is abelian, and I have some locally complex structure on it. So I denote by G hat, this is the set of continuous homomorphism from G to the unit circle T. So these are one-dimensional unitary representations of the group G. Then we know that if it, by Pentragian duality, so if we take the dual of the dual, so then we can get back our group G. So if I instead consider continuous homomorphism from the dual of G, not to the torus, but to complex numbers except zeros, so I will call this set of such homomorphism for the abelian complexification of the group P. And it's quite easy to see. Then we have the abelian complexification of R. It will be the group of complex numbers. If I consider the complexification of the torus, so I will get C minus 0. So this multiplication is the group structure. And if I take abelian complexification of the Z, so I will get that back. So complexification of a compact group. So I fix a compact group, and I will consider so-called left regular representation of G. So if I have a group G, so I have a compact group G, so I have a Haar measure, so I can consider this Hilbert space L2 of G, and I consider the left regular representation, which is given in this way. And to this representation, so I relate algebra, so it will be a von Neumann algebra of the group G, which I get just taking the bicommutant of the set of the images of the group G under this left regular representation, or I take linear span and take a strong closure, so in strong operator topology, so I will get this von Neumann algebra. If I have a G is compact, so I will now denote by G hat. This is the unitary dual of G. So the unitary dual of G, I mean the equivalence classes of unitary representation, unitary irreducible representation of G. And I treat them as a set of irreducible. I take representative in each equivalence class and fix of this representative and consider. So it's known that if G is compact, so then any irreducible unitary representation, so it's finite dimensional. So it's just representation in matrices. So I will denote by dp. So this is the dimension of this representation space. And it's known that this less regular representation, so it's quasi-equivalent to the direct sum of this finite dimensional reducible representation. And Vn of G can be treated as such L infinity sum of linear operator on HP. HP is finite dimensional, so this is just L infinity direct sum of matrix algebras of dimension dp. Then I consider the following algebra. So it's an algebra of trigonometric polynomials, or we call it algebra of trigonometric polynomials. So this is the span of matrix coefficients of elements in G hat. So I take the irreducible representation and consider matrix coefficients of this irreducible representation. And then I can also write the trig G as such a direct sum of P of G, where this is just the coefficients of the representation P. So Fourier transforms, so it's an important tool. So and it's important even in the context of the compact group, not only a abelian group. So if I have an element in trig of T, I can consider such operator valued Fourier transform U hat P, which is defined in this way. So it will be the value of this. It will be a matrix in this of dimension dp in this space of linear operator HP. So any element Q, I can associate such a family of U hat P, and one can easily check that I will have only finite number of non-zero element in this sequence parameterized by elements in the hat. And then the linear dual space of this trig G, so it can be identified with this product of matrices, and it's convenient to use the following duality between elements of trig G and the elements of this product. So there is some formula, and yeah, so this element they are related to Vn of G. So because Vn of G I identify with such a infinity sum, but it's not really there, so it's a little bit more, and it will be the set so-called of affiliated elements of Vn of G. So I will talk about this a little bit later. Yeah, so compact group complexification. So it was proposed by McKenna, 79, and it was studied further by Cartwright and McMullen in 81. And they defined a complexification of this compact groups, a very abstract complexification, so as a set of multiplicative linear functional on trig of G. So this is the set of characters of trig of G. So we defined T, which are non-zero elements in this product which satisfy this condition, so that it's multiplicative. So I will have that T is in this complexification if and only if. So I can write it in this way. So if M is the multiplication on this space of functions, so this is a space of functions, so we can multiply them. So then M dual of T should be equal to T tensor of T. So just remember this formula. And then we also can see the group G inside of GC if we identify G with the following set of operators in this product. So and it will be, we can identify it with the image here. And the theorem it goes back to Crane, Tanaka, McKenna, Cartwright, McMullen says that GC is a group, so we can multiply the elements. So this is the usual multiplication. So we multiply each element pointwise. And then if we take the intersection of with the full Neumann algebra, that is with the direct L infinity direct sum of this LHP, so we will get the group G. So it will be coincide with the left regular representation image of G. And we have also if T in GC in the complexification. So if we take the positive part of this T, meaning that we take a positive part of each operator, each matrix TP, so then we will also get B in GC, and we have that this one is will be in the group G. So we have such a decomposition GC, so it's equal to G times some positive part of GC. Why complexification? So we can consider the following small gc, so which are elements. So this is derivations in E. So we consider element X in the product which satisfy this condition on a trig of G, and it can be formulated in the way that the dual to the multiplication applied to this element X, it should be equal to that one. And then we consider G to be skew adjoint elements of this stuff. And then we have the GC, it will be the complexification of G. And GC, it will be Lie algebra, and G, this is a real subalgebra. And the commutant here, the Lie bracket is just the commutant defined on the set of operators. And we have also the theorem of Cartwright-McMullen, so which says that if you take X in GC, so then and we take the exponent of this Tx, meaning that we take the exponent of each function, so it will be in GC, so it will be like the exponential map between GC and the group complexification C. And if we take element in the real subalgebra, so you will get that exponential map, so it will send the element to the group G. So we have that this one, it would be the positive part, and this one, it will sit in G. So in case G is the connected Lie group with Lie algebra G, then GC is just the Lie group of the algebra complexification of GC. And we have these examples, so that the complexification of SU and C, so it will be isomorphic to SL and C. Complexification of T, so it will be this one. G is abelian and compact, so you will have that these two concepts, which abelian complexification, this compact complexification will be the same. Yeah, general case, how we can generalize this complexification to general case. Yeah, we consider G locally compact known group G, so, and the same left regular representation, the N of G is this our group von Neumann algebra. This group von Neumann algebra, it has an extra structure, it is an Hopf algebra, which means that there is some additional structure except for multiplication addition, so there is also a so-called co-product on it. So we have a map from Vn of G to the tensor product of Vn of G, Vn of G. It sends the image lambda s to the tensor product lambda s tensor lambda s. And it has also the antipode, which is responsible for inversion of the element in the group. So it sends lambda s to lambda s inverse. If G is abelian, then Vn of G, so we can identify with L infinity G hat through the Fourier transform, and then the coproduct will be given just on the function. It will be given in this way, so you'll get function into variables, and it will be a value of the function f on the product. So it's somehow coproduct encode the information about the product on the group G, and antipode is given in this way. So it's like decode the inversion. So coproduct here it is given in this way, but it can be described we can give a formula for any element in Vn of G, not only element of lambda s. There is so-called the fundamental unitary W, which implements the coproduct, and it is given in this way. So we can define the coproduct for all x in V and G, and this is given by this formula. And W has a nice formula, so easy formula, which is given in this way. So it's a unitary operator acting on the tensor product L4G with L4. Yeah, the fact that we have that lambda G, the image of lambda G, we can find it as using the following. So it's all elements in the this algebra such that gamma of x is equal to x tensor x. So remember, we had some similar formula when we defined the complexification. So we had this dual to the multiplication map. So of x, it should be equal to x tensor x. So we have here something similar. Yeah, I need also something which is called affiliated elements to von Neumann algebra. So it's some kind of closed, densely defined, but unbounded operator on T is such that U star TU is equal to T for every unitary U in the commutant of the von Neumann algebra M. And I will denote affiliated elements by M bar. So for example, if I have L infinity as my von Neumann algebra, so then measurable function, so it will be the element affiliated to this algebra. So since gamma of x is given in such a nice way, so I can extend it even to the affiliated elements, and then I define the abstract. So it lambda complexification of the group G is the set of all x. Now I consider not only elements in V and G, I consider elements, unbounded elements affiliated to V and G, which satisfy the same condition that gamma of x is equal to x tensor x. And yeah, so if we remember what was told about the compact group, so we can easily realize that if G is compact, that this complexification is just coincide with Cannon-Cartwright-McMullen abstract classification PC. Yeah, and I have similar result. I can introduce Lie algebra, so which is given in this way, and I have such exponential maps. So I have a bijection between this Lie algebra and the positive part of the complexification. I have that my complexification has a decomposition. It can be written as lambda s, something coming from the group G, and this exponent which is coming from this Lie algebra. And if G is a connected Lie group and with Lie algebra G, then I have that lambda. This is just the image of infinitesimal representation lambda. So from the group, we lift this representation to the Lie algebras and take the images. And GC lambda is given in this way. So D lambda is as the differentiation, we find it in this way. So it's nice to know also, we haven't studied, but this would be nice to know whether GC lambda always a group. So we have it in the case of compact groups, but in the non-compact group, we have certain problems because not always we can multiply those elements, the unbounded elements, so, and they may have disjoint domain where they define it. It's interesting to know where there is a good locally compact structure on GC, and whether G is connected Lie group, whether there is a connection with the universal, so-called universal complexification of G. Okay, so I want to apply this knowledge to study some algebras related to the group, and my object is I will start with the Fourier algebra of AFG. It's important object in abstract harmonic analysis. And it can be defined also algebraically in the following way. So the Fourier algebra A of T of locally compact group T is the pre-dual of the Vn of T with the multiplication given in this way, where gamma is the co-product on Vn of T. I can also give it as more easy to understand for analysis, in analysis for people from analysis, so that A of T can be given also as a space of functions in C0 of T, which is just the convolution of two functions in L of T. And this is a commutative algebra with pointwise multiplication. We having a representation in this way, so we can introduce the norm on it. It will be given in this way. And we have the duality with Dn of T. It's given in this way. In particular, if I take the duality lambda x with u, so I will get this representation in u of x. And an important fact about this algebra is that the spectrum, so the Gelfand spectrum, the non-zero multiplicative linear functional of A and T, so they are homeomorphic to the group G, and the homeomorphism is lambda x tends to x. This makes this important fundamental connection between algebras, defined algebra function on G, and the group G itself. Okay, so, and this correspondence can be easily seen in the following way. So if I have x is a character of A of G, so I write what character means, so it will be this way, and then I can rewrite it here, so like this, and then it's like this, and I will get that my gamma x should satisfy x tensor x, and there, according to the fact I mentioned, so I will have that x is should be the image of the group element on the left regular representation. Yeah, so if G is abelian, so I have this A of G is just the image of Fourier image of lambda of G. If G is compact, so I have the trig G is always sits in A of G, and it can also be seen as the operator Fourier transform in this way, but maybe I don't say more about this. Yeah, weight is Fourier algebra. So I want to, so I have a connection between Fourier algebra and the group T through the spectrum. So now I want to introduce weight and see whether there exists some connection of this weighted Fourier algebra to something. And of course, I want to make a connection with the complexification, which I just have defined. Yeah, a scalar weight function on G is just the function which satisfies this submultiplicative condition. If I also assume that it is bounded below, so I will have that omega will be an element in L infinity of G, and then this condition, so it can be rewritten through the in this algebra in using the coproduct as omega times omega is less equal than the coproduct by 2 omega. Yeah, so weights, an example of weights, it could be given in this way. So if G is abelian and W is a weight on G hat, so we can consider some weighted L1 of G. This is a Banach algebra with respect to convolution, and then I can define a G W as the Fourier transform of this space, and this can be given. It's also equal to the following. So I take L1 G hat and then multiply by this weight inverse omega. Yeah, in general case, so I define weight on the dual of G as element in Vn of G such that, so I rewrite that condition write it in the following way. And it's equivalent to saying that we have that omega tensor omega is equal to gamma omega and omega. This is in Vn of G. So this is a special element. It also has some special conditions. So it's so-called Juko cycle. And I put some more condition that the canal W star is equal to 0. And then I define my Fourier algebra is just the following in the following way. So since Vn of G is a dual of the A of T, so I have the action of this of each dual element on A of T. So I take this action omega to A of T, and I will get that this is Hub algebra of A of T, because if I write the multiplication, so I will get this way. So using the condition that omega tensor omega is equal to that one. So it's a commutative Banach algebra, and that's called the Berling-Fourier algebra. And if I introduce the following norm on it, and the duality is given in this way. Yeah, so as I told, I want to know the spectrum, and I want to know to see the relation to the complexification. Yeah, let's look at the complexification for the compact group G. So if G is compact group, then I can see the trig of G, so which I defined in the beginning for the compact group. So it's always sit in this algebra as a dense subalgebra. So therefore, any multiplicative character on AG omega, so it will be a multiplicative functional linear function on trig of G. So therefore, we will have this connection with the complexification. And more formally, so if I have a sigma, so in the spectrum, so which I think as an element in Vn of G, so because the dual of Ag omega is Vn of G, so I write it in this way. So it's written, it's L infinity sum of matrix algebra. So the condition, if I write the condition about multiplicativity, so I will get the sigma omega inverse. It should be the element, it should be multiplicative element on trig of G. So it will be in G of C. And in this way, so if I identify Vn of G with this set, so I will have the spectrum, it will sit in the complexification. So maybe just in just commutative examples, so if I have G is equal to T, then the dual of T is Z, so my weight, so it's enough to define it on the dual, so on Z, so I can define such exponential weights. And then the complexification, it would be function from Z to C star, so I will write them as a sequence, which satisfies this condition. And this is the solution to this one is just the powers of some complex numbers. So the spectrum, it will be given, it will be in C star. And then we have the condition, so it's not all element in the complexification, but those elements, so that when I multiply them with omega, so I have to get a bounded element in Vn of G, so in L infinity here. So I will get the spectrum of this, it will be larger, it will be something around T. Yeah, so general G, so I consider omega in Vn of G, it's a weight inverse, and I consider this cocycle, which satisfies this condition. Then the spectrum of Ag omega can be identified with the following set. So the spectrum, so these are elements in Vn of G, non-zero, which satisfy this condition now. And it can be seen from this calculation. Write down what it means, and we will get this. So we want to find a solution. So in order to find the complexification, to find the spectrum, we have to find the solution of this equation. So this is a similar equation which we have for the weight. So, but except for the condition that the kernel of omega was 0 here, so sigma could be non-zero, has a non-zero kernel. So we have to find this solution. And our guess, so like in the compact case, so that sigma divided multiplied with omega inverse, it should be something coming from the complexification. And formally, so it is really this case. The sigma is in the spectrum if it is of this form where T is in the complexification. Yeah, so here we have some formal calculation, and if we in this complexification, we have so-called the closed operators. So therefore, we have to show actually that this operator defined in this way is closable, and this is really the challenge in the more analysis. But these conditions boils down to the equality, algebraic equality. So S here, so this is the antipode. Yeah, so we have to show that any element in the spectrum satisfy this condition, and there is a clear explanation, or some intuitive explanation why we should expect this, because antipode is responsible for invertibility of element in the group, so it will be should invert also element in the complexification. And then if you write this condition, so you will get that this should be true. Unfortunately, we could not prove this in general case, and there is some obstacle connected with the antipodes, so it's not completely bounded for those who knows this, but we could still derive the condition for quite a big, wide number of groups. Sorry. So we could prove that spectrum in the complexification and G is compact when G is virtually abelian, and G is a separable type 1 group, and the omega space invariant almost everywhere. Then if almost all our source is weight, it comes from subgroups, from abelian subgroups. On abelian subgroups, we can write a lot of weight functions, and those are examples. They are coming from here. So, and we have that if we have a weight which comes from a weight on a abelian subgroup. So here, so there is explanation of the extension of the weights from the subgroup. Then we have that the spectrum is in the complexification. Yeah, and yeah, last slide. So we can not only give that the information that the spectrum is always in the complexification for many groups, we can also identify it explicitly. So if we look at G, the group is one of those lists, and if we have a abelian subgroup and weight on this abelian subgroup and weight coming from the weight from abelian subgroups, so then the spectrum we can identify in the following way. And here we can identify it up to the spectrum of the Fourier algebra on abelian group, and this is quite an easy object to do. So yeah, I have example of Heisenberg group, but probably I skipped it. And thank you very much.